Hello, everyone. Welcome to our first talk of the seminar series. Before I introduce our speaker, if you have a question, please push the button, which is, how does it call? Raise your hand. Then we will let you ask your question. All right. So it's my pleasure to introduce today's speaker, Tom Hutchcroft from Caltech. And Tom gonna tell us about the critical long-range percolation. Please, Tom.
Thank you. Thanks for the invitation. It's very nice to speak here. Finally, after however many years this has been running for. It's also nice to see, some familiar names in the participant list, people I haven't seen in a while. So, hi, everyone. So I'm going to be talking about critical long-range percolation. Actually, it's going to take me a while to get onto long-range percolation because I want to start by talking about nearest neighbor percolation. In fact, I'm going to start even more broadly than that. And I should mention, by the way, this talk is going to be quite similar to my ICM proceedings. So which I just appeared on the archive. So if you want to see a sort of written up version of this talk, you should look at that too. Okay, so what are we studying? At a very broad level, we're interested in phase transitions and critical phenomena. So what is a phase transition? It's when you have some kind of system with many, well, they could be particles, but components that don't have to be particles. They could be like people in an economic or disease spreading system, something like that. And these components interact with each other according to some usually fairly simple rules that are described by some parameters that you can vary continuously. Okay, and a phase transition occurs when, as you vary these parameters through some special value, the behavior of the system changes in some kind of qualitative way on a large scale. So, we're all familiar with when you boil water in a kettle or freeze water in your freezer, right? As it crosses a critical temperature, right, 0, 100 degrees C, it will completely change its structure. Okay, and but phase transitions occur all over the natural sciences and also in many other places as well, like in epidemiology. And understanding phase transitions has been a huge topic in modern probability theory, and it's still very poorly understood. So, for example, this is not really related to my talk, but it's an open problem to prove that water freezes when it's cold. Okay. So this talk is more specifically about critical phenomena. So what that means is that many systems, when you tune them exactly to the point of phase transition, they exhibit this kind of rich fractal-like behavior. This is not true of all critical systems. For example, you don't really see things like this in water, freezing or boiling in normal circumstances. There are some points that you wouldn't see in your home where you can get interesting critical phenomena to happen in this kind of systems. But many systems do exhibit this kind of very intricate behavior at and near their critical point. So this is a simulation of some critical 2D percolation stuff done by Jason Miller, and you can see all these, fractal-like boundaries and fjords and things like that, and we'll see more examples of this soon. And, generally speaking, we know how to understand critical phenomena pretty well now in 2 dimensions after, a few decades of development, and also in high dimensions where, as we'll see, it tends to be that critical phenomena just becomes easier to understand in high dimensions, and it's very poorly understood in between. So especially dimensions 3, often dimension 4 is hard too. Okay, so I'm going to be talking about these things in the context of percolation. So percolation, you can think it's maybe the easiest to write down mathematical model of a system undergoing a phase transition. So how does it work? So you have a graph G, and in this case we started with a square grid, say. And we're going to be doing bond percolation which means we delete edges. You can also do site percolation, which means you delete vertices. So we're flipping a coin independently at random for each edge of the graph. It has probability P of being heads, 1 minus P of being tails. We delete every edge where we see a tail, keep every edge where we see a head. Okay. And we're interested mostly in the geometry of these connected components that are left over after doing this. So some standard jargon at the field is that we call the edges we keep open, the edges we delete closed, and the connected components of the random graph we have left, the clusters. And I think in this example, P is like 0.45, a half, and 0.55 or something like that. So you can see P is not massively different in the three cases, but you can see that on the right-hand side, the graph looks much better connected than on the left-hand side. Okay. So sort of the first basic theorem about percolation that makes the model interesting in some sense is that it undergoes a phase transition. So these are phase transitions that are cleanest to define in infinite volume, and we'll restrict to that case for this talk. Sorry. So if we define theta p to be the probability that the origin is in an infinite cluster, i.e. an infinite connected component, then we can define the critical probability to be the infemal value of p where this is positive. So actually, the existence of an infinite cluster is a tail event. It's a 0-1 event. So you could equivalently define this to be the infemal value of p where an infinite cluster exists almost surely. And again, the first basic theorem is that in dimension strictly larger than 1, so if you have a grid, not necessarily a square grid, like any kind of d-dimensional grid, if you're in 2 or more dimensions, then PC is strictly between 0 and 1. So you have a phase where there are no infinite clusters, followed by a phase where there are infinite clusters. Of course, in 1 dimension, you never have this. PC is just equal to 1 for uninteresting reasons. And in fact, in this particular example I have on the screen of the square grid, it's a theorem of Harry Keston from, I think, actually from exactly 1980. Or it's really Ted Harris had earlier progress on it, so often called the Harris-Keston theorem. The critical probability for bond percolation on the square grid is exactly 1/2. So this is an important theorem. It's very useful if you're studying percolation on the square grid, or in a minute I'll show you some simulations. And of course, if you're doing simulations, it's very useful to just know what the critical probability is. But this shouldn't give you the wrong impression, because it's quite atypical. In this case and some other planar cases, you can compute PC exactly. But for example, if you're working on the 3-dimensional cubic grid, there's no reason to expect that PC has any sort of closed form expression at all. So it's something, usually if you want to study percolation outside of a few of these special planar examples, you probably have to do it without actually knowing the value of PC. You just know that it's defined implicitly as the point where the phase transition occurs. Okay, so what kind of questions do we want to study about percolation? Well, there are many that one can study, and this talk is really just going to focus on the problem of the critical behavior itself. So we want to say, we know PC is the boundary of these 2 phases where you do or do not have infinite clusters. What can we say about percolation exactly at the critical point? Okay, and the first basic qualitative conjecture, which is still open, is that there's no percolation at criticality, i.e. you do not have any infinite clusters at criticality. Or the more jargony way of saying this that I'll probably say, so I better tell you what it means, is that the phase transition is continuous. That just means that there are no infinite clusters at criticality. Okay, and this is very open in dimension. It's extremely open in dimension 3, 4, and 5. There are some hope that some techniques might work in dimension 6. And I'll say more about the cases where it's not, or less open, in a minute. Now, on the other hand, this talk is not really about this problem. So it's about the problem we would like to solve after solving this problem, namely to understand quantitatively or in detail, like, what do the finite clusters look like? Okay, so what we expect is that at the critical points, you only have finite clusters, as this conjecture says, but it should be pretty easy for them to be big, and they should have like interesting fractal-like geometry. So, for example, the probability the origins in the cluster is 0, so the probability it's in a big cluster decays. But if you look at a big box, you expect to see macroscopic clusters on that box, like, for example, clusters that connect one side of the box to the other, things like that. Okay, now there's a few ways you can try to study the geometry of these large, like fractal, like critical clusters. So one way is through scaling limits. So what that means is you take the lattice spacing of the system, like instead of working on the integer lattice, you work on like the epsilon lattice, and you try to say, okay, maybe I can make sense of some kind of limit of what critical percolation is as that lattice spacing goes to 0. Okay, and if you can do that, then you can probably understand everything. A slightly weaker notion of trying to understand what's going on is through the language of critical exponents, which is what's on this slide. So the idea basically is that we expect at criticality, so critical systems are often characterized by scale invariance, meaning that, once the lattice spacing is really small, well, I was just saying you expect to have a scaling limit, right? So ideally you could take the lattice spacing to 0 and recover some kind of continuum critical percolation, whatever that means, like on real Euclidean space. And this means that you shouldn't be able to really tell what the lattice spacing is once it's small enough that you can't see it, that you can't just obviously see how big the lattice is. And scale invariance goes hand in hand with power laws. Power laws are like the manifestation of scale invariance for functions of a single variable. And so what we expect is that various interesting quantities are described by power laws. And for example, some of the most important ones are what we call the 2-point function. So the probability the origin is connected to X, that they're in the same cluster at the critical point. This should decay like some power of the distance of X to the origin. K will be my notation for the cluster at the origin. So you could either look at criticality and look at the tail, the probability it's large. This just means that the number of points in the cluster. You could look below criticality and see how its expected size blows up as you approach the critical point, all of these kind of things. And, there are tons of critical exponents you can define. I just put a few here. And basically the story is that in high enough dimensions, the critical behavior of percolation becomes much simpler. And this is reflected in part by these critical exponents having these simple explicit values. So for example, in high dimensions, we expect the 2-point function, so the probability the origin is connected to X, to decay like X to the minus D plus 2. And you should think this is the same scaling as the Green's function, which you could think of as if you start a random walk at the origin, what's the probability it hits X? Actually, in percolation, it's better to think that this is like the branching random walk Green's function. So I'll say something more about that in a minute. And similarly, this thing with 1 over root n scaling at the probability of having a large cluster in volume in high dimensions, that's the same 1 over root n you would get in a finite variance branching process. So one way of understanding these things is that percolation in high enough dimensions, the lattice is like so big that the model doesn't really feel that it's on a finite dimensional lattice at all. It starts to behave the same as it would if it was in a setting with no geometry, whatever that means, or trivial geometry, like a binary tree. You would get similar exponents and or a complete graph where you're doing Oda-Shreni, something like that. Okay, and basically, with an important caveat that I'll explain in a second, this is a theorem. These things are all proven. Essentially, although it's not just this one paper, but the main input came from a very important work of Hara and Slade in 1990, who developed a technique called the lace expansion, which I won't really get into in this talk, that was introduced originally to study a different model called self-voiding walk by Bridges and Spencer. And the lace expansion is like a systematic way for many models that you can, like I should say, now that it's been developed by Har and Slade and they applied it to many models, it's now like a systematic method you can apply to many models to prove this simple mean field behavior in high enough dimensions. And the main caveat is, so I should say, by the way, this basic story about how you have what's called the upper critical dimension, which for percolation is 6, above which the critical behavior becomes simple like this. This happens for many, many models. The value at the critical dimension is model dependent. So for percolation, it's 6. For many other things, it's different. So Ising model, self-voiding walk, it's 4. The contact process, it's 2. For lattice trees, it's 8, and so on. It tends to be an even number, actually, but it's you can get lots of different values at the critical dimension. And the main caveat here is that the results don't just need that D is at least 7. They need some numerical assumptions on the lattice. So if you want to work with the standard hypercubic grid, then you need the dimension to be very large. They needed at least 19. Now with computer-assisted proofs by Pfitzner and van der Hofstad from more than 10 years ago, now they got it down to 11. On the other hand, if you're in just 7 dimensions, which is minimal, you can get the proof to work if you change which lattice you're working with. So if you work instead of with ZD, you work with what they call the spread out lattice. So instead of just having edges between nearest neighbors, like in the hypercubic grid, you say, I'll have some big parameter L, and I'll say I connect 2 points by an edge if they're distance at most L from each other in space. Okay. So that's the high dimensional story, and I'll have more to say about that in a minute. What about low dimensions? Well, the idea is once you go below the critical dimension, the model really starts to feel the geometry of the space in a non-trivial way. And one way this manifests itself is that the exponents change. Or you should think, I'll explain in a minute how we can think of percolation as kind of an interacting version of branching random walk. And this interaction becomes significant and it really changes what's going on at large scales in low dimensions. And there's really only one case that we understand this fully, which is site percolation. Again, site means you delete vertices rather than edges on the triangular lattice. And in this case, we know a lot of the exponents. And they take these funny rational values. So you get 5/24 for the 2-point function, 5/91 for the volume tail, and so on. So this is a culmination of work by a lot of people, a lot of famous works as well, I should say. And also these exponents were all conjectured in the physics literature at least a decade before they were proven by mathematicians. They were predicted by Ninhues. Okay. So one thing I should mention with all this is, we expect with all this percolation critical phenomena, and this is a big story in critical phenomena more broadly, that you have the phenomenon of universality, meaning details like which grid, like whether you work on the square or triangular lattice, they shouldn't affect the critical behavior at all. That's very clear empirically. It's well understood by physicists and with heuristic methods and so on. But proving universality remains a major challenge. So in high dimensions, the proofs just sort of are naturally universal, aside from these numerical caveats. But in low dimensions, we really only know how to prove these things fully in a single example. Okay. And you can imagine 2 dimensions is very special for a variety of reasons. You have the restricted topology of plane curves. You have complex analysis, which turns out to be very relevant for these developments, and so on. So this fact that you get these strange, they're complicated, they're not these very simple values you get in high dimensions, but they're still rational values of the exponent. This is a very 2-dimensional phenomenon. And, in 3 dimensions, probably the exponents are transcendental. There's just no reason to expect them to have any nice structure or even to have closed form expressions of any kind, let alone algebraic ones. Okay. So I'll say more, but the short story is that in 3, 4, and 5 dimensions, these things are very hard to understand. Even if you're a physicist and you're not trying to prove anything, you just want to have heuristic methods, they're still very hard to understand. One interesting case where we have conjectures but not theorems yet is 6 dimensions. So 6 is exactly the critical dimension for percolation. And again, it's a general feature when you tune models exactly to the critical dimension, you expect to have almost mean field behavior, which means like you expect to have usually the same scaling limits as in high dimensions, which will be some simple explicit thing. For percolation, that will be super Brownian motion. I'll talk about more in a bit. And you have the same exponents, but you have to put in some logarithmic corrections to scaling to get things to come out correctly. And in fact, in percolation, since the 70s, there have been exact conjectures about what these powers of log are. So, the 2-point function, for example, is supposed to be larger than the Green's function by log to the power 1/21, and the volume tail is supposed to be larger than the high dimensional, the 1/√n thing by log n to the 2/7, and so on. And one thing you can imagine here is that these things are very hard to verify numerically, right? I mean, it's you're never going to tell the difference between a log to the 1/21 and a constant realistically. Okay. So I was saying about how in high dimensions you get this relatively simple critical behavior, and in low dimensions something more complicated happens. But rather than just thinking about it as some number changes, like the value of the exponents, I want to emphasize that this is really reflecting a qualitative change in how systems are looking between high and low dimensions. In fact, there are a number of ways of thinking about this. So one thing to start with is I can say, well, in high dimensions, if you take a big cluster, it's basically going to look like a tree. I apologize for how blurry this image is, by the way. I don't know why that happened, but anyway, so in other words, if you take the cluster at the origin, you're in high dimensions, critical percolation, and you condition it to be very large. Of course, it's not a tree, right? I mean, you're doing percolation on a grid. You're flipping coins. You have all these little cycles of length 4. There'll be a positive density of cycles of length 4 in this picture, but they're not important to the macroscopic geometry. So you don't have macroscopic cycles. So if you take a big cluster, you rescale it by its diameter, it will have all these cycles, but they'll be negligible on the scale of the cluster. And so you expect it to converge to a tree. On the other hand, in low dimensions, the cycles are like super important. You have macroscopic cycles all over the place. So this is a simulation of, I think, the 5 largest clusters in percolation on a big, critical percolation on a big 3-dimensional box. And you can see these clusters, each of them are colored on a different gradient, so you can see them separately. They're pretty chunky, they don't look like trees at all. In fact, even that the density is going to 0 is not completely obvious. Well, maybe I just didn't do a big enough simulation. Okay. At the critical dimension, by the way, you still expect to have this picture on the right, but the largest cycle should only be small by like a 1/power of log factor. So again, if you're doing a simulation, 6 dimensions wouldn't really look very much like a tree within the system sizes that you'd be able to simulate, but it would eventually look like a tree at very, very large scales. Okay. And okay, let me switch to showing you some videos. So the one way I like to think about this, that I think is somehow the best way of thinking about this distinction between high and low dimensions, is that we can think of percolation as an interacting version of branching random walk. So I'm going to play some videos of branching random walk while I explain what branching random walk is. Okay, so branching random walk is, you can see the video, right? Yeah, okay, good. So branching random walk is a Markov process where at each step you have finitely many particles. Now in this part, there can actually be more than one particle on a site. I just didn't make the simulation very well, so you can't see that. But at each point in time, there are finitely many particles. Each one of them is on a lattice site. At each time, each one of them splits into a random number of offspring particles. and each one of those particles lives in on a random neighboring vertex. So the particles are randomly branching and randomly moving at the same time. By the way, usually what happens if you do this at criticality is it just dies quite quickly. So these videos I'm showing you, I conditioned it to survive for a reasonable number of steps so that you had something interesting to see. Okay, so again, I'll show you one more video of branching random walk. Well, I'll wait for this one to die, but hopefully the definition is clear. The particles are randomly splitting, randomly moving, and again, it would the probability it survived for 383 steps, as it did in this example, is a roughly 1/383. So this was an atypical outcome, but otherwise there wouldn't have been much to see. And here's an even more atypical outcome. Oh well, we don't want to watch the whole thing because it's 5 minutes long. In this one, I tried to make it so that the vertices with more particles show as a larger square, so that you can see, okay, some of that they're actually building up density. Okay, and you could imagine so this is critical branching random walk. So that's when the average number of offspring each particle has is 1. Okay, and this will die almost surely eventually. And again, that it's been conditioned to survive for a large number of generations. Okay. And you can imagine that there is some well-defined scaling limit of this, and indeed, this is something that has been understood for a long time. So, of course, to take the scaling limit, you also need to do this conditioning or something like that to make it non-trivial. And the scaling limit is something called super Brownian motion. So this has been something studied in probability for decades now. It's related in important ways to various stochastic differential equations. And the scaling limit super Brownian motion is a process where at each time you have a measure which is made up of like infinitely many infinitesimal particles that are each continuously branching and diffusing. Okay. And okay, I won't show you the rest. Now, what about percolation? So let's now view percolation in a similar way to how we viewed branching random walk. So what I'm going to do is I'm going to do a breadth first search of the percolation cluster. So at each step, this red cloud, these are the particles that I just found were in my cluster at the previous step. Okay, so what are we doing when we sample percolation? Sorry, this goes a bit fast, this one. Well, at each step, we're saying each particle in the boundary is kind of trying to do what the branching random walk does, right? So it looks at each of its neighbors and it says, I flip a coin to decide if I have an offspring particle there, right? Now, the difference with branching random walk, and let me show you the bigger percolation simulation. The difference with branching random walk is that I'm not allowed to reuse the sites that I already went to, right? And that's very clear in the simulation. But in fact, that's the only difference. So you can think that percolation viewed in this way, where you're like exploring it via breadth first search like this, it's exactly like a self-interacting version of the branching random walk, where the interaction means that you're not allowed to reuse sites that you already used at previous steps. Of course, to make up for that, the critical value is larger, right? It's like in branching random walk, if you have one particle at the origin, at criticality, it has one offspring in expectation. In percolation on the square grid, the critical probability is 1/2, and the degree is 4, right? So if you just have one particle by itself, the expected number of offspring it has at the next step is 2. So this higher degree in the absence of the things around you blocking you is compensating for the fact that you have things blocking you a lot of the time. Okay. And one thing that's clear, in fact, I can even run these two simulations next to each other, right? Because you can see my whole screen. One thing that should be clear from this is, well, these two things don't look similar at all, right? And indeed, that's because this is a two-dimensional simulation, and percolation and branching. Okay, you can view percolation as a branching random walk, but this interact as an interacting branching random walk. But in 2 dimensions, this interaction is very strong. I mean, it completely changes the behavior of the process, right? I mean, you can see that this explored region is really big. I mean, the branching random walk is like mostly like bunching back up on top of itself all the time, and you have these dense regions that are just evolving. Whereas here this excluded space constraints is completely changing what's going on. Okay, now one way of understanding this distinction between high and low dimensions is that once you get to dimensions strictly larger than 6, which is of course much harder to show you a good video of, this fact that percolation has to avoid its past is really not making very much difference anymore. And in fact, if you were to do this, and I say this version of the scaling limit where you're looking at these breadth first generation layers and trying, this has not been done yet. But in forthcoming work with Arthur Blanc-Renaudy, and I guess I'll switch back to my slides, we show that in high dimensions, percolation does have the same scaling limit as branching random walk when you look at the whole cluster of percolation versus the whole collection of all particles over all times in the branching limit. So this is the integrated version of the scaling limit. Okay. And in particular, if you look at the cluster just as a metric space, like with its graph metric, it converges to something called the continuum random tree. That's a random fractal tree constructed by Aldous. It's the same scaling limit you get by just picking a uniform random tree with n vertices. And one way you can think about this super Brownian motion thing, by the way, is that you first sample the continuum random tree, which is the scaling limit at the genealogy of the particles in the branching random walk, and then you just embed that into space using Brownian motions. Okay, let me tell you one more way of thinking about this distinction between low and high dimensions, which is in terms of what the validity or not of what are called the hyperscaling relations. So here's the idea. So as I said, if you take a big box, in critical percolation, you always expect there to be, even though the clusters will have like zero density, right? That morally speaking, zero density of the clusters at criticality is equivalent to the continuity of the phase transition, i.e. not having infinite clusters at PC. So although the clusters have zero density, you do expect them to be macroscopic, right? So you expect to have, for example, clusters connecting two sides of a box, or the middle of the box or the outside of the box, things like that. And in low dimensions, the idea is that the number of large clusters, however you precisely define it, will be order one. It won't blow up. It'll be random, so it could be anything with any finite number with good probability, but it'll be order one, i.e. tight, as the side length of the box converges to infinity. And in high dimensions, what you expect is that there are actually a large number of large clusters. So in fact, this is understood quite well. You actually get r to the d minus 6. So for example, if you looked at the number of clusters that go from the middle of the box to the outside of the box, this will grow as a power of r to d minus 6 when d is bigger than 6. And so this is really like a qualitative change in what's going on in percolation. And one thing I like to stress here is that these are sort of both useful properties. They're both good things to have for your understanding. Of course, in low dimensions, aside from in 2 dimensions, this is still conjectural. In low dimensions, this fact that you have the hyperscaling relations is, the fact that you have order 1 clusters gives you these things called the hyperscaling relations. And an example of that, let me see if I can, I lost the control panel for the, yes. Let's see if I can. So one example of this would be that, oh no, this is going to take way too long to write with my trackpad. The probability X is connected to Y. In low dimensions, well, you have 2 points and you want to connect them to each other. And in low dimensions, there's like order 1 large clusters on each scale. So connecting the 2 points together should be roughly the same as them both just connecting to the right distance. Like if they're both getting far enough, like on the scale of the distance between them, then they have a good probability of being connected in low dimensions, but not in high dimensions. And in fact, so this gives a relation between two critical exponents, right? You have the exponent for the decay of the point-to-point connection probabilities, and you have the exponent for the decay of the what's called the one-arm probability, so like reaching the boundary of a large box. In fact, this is one way that you can compute that the critical dimension should be 6 for percolation. And the idea is that, well, at the critical dimension itself, you probably, both of these things should be happening simultaneously up to some logs. So, in the critical dimension, probably this number of large scales on scale R is some power of log. And, this hyperscaling relations are not quite true because there are some logs that make them go wrong, but they're true at the level of the exponents. And, in high dimensions, each of these arm events here decays like 1 over r squared. That's like what it would be for a branching random walk. And this guy, the connection probability is the Green's function. It's r to the minus d plus 2. Right? So in fact, one way you can compute that the critical dimension should be 6 for percolation is you say, well, at the critical dimension, I should have these mean field values at the exponents, and the hyperscaling relation should hold. So at the level of exponents, this probability should be like the product of the square of this probability, right? Because you have one arm event here and one arm event here, right? So in other words, you get minus d plus 2 equals minus 4, which means d is 6. Okay, let me now clear these. Good. All right. Okay. Okay, so there's one thing I haven't really said yet well, I said that dimensions 3, 4, and 5, they are difficult to understand. So, and as I said, that's still true if you're a physicist, although the physicists still certainly know more than we do. And they do have a couple of nice ways of reasoning inexactly about critical phenomena in dimension 3, for example. So for a long time, really, the only way they had of doing it was something that's called the epsilon expansion. Often, I don't really like this terminology because, every expansion is an epsilon expansion. So I'll call it the Wilson-Fisher expansion, which is sometimes also used. So there was a very influential paper of Wilson and Fisher, I think in the late 70s. And they said, okay, 3-dimensional Ising, so for Ising, 4 dimensions is the critical dimension. Like 3 dimensions is very difficult to understand. 4 and higher, at that point, they already knew how to understand well. So they're like, well, maybe instead of understanding 3 dimensions, let's study the Ising model in 3.99 dimensions. Okay, now, of course, your first complaint as a mathematician is probably, well, that doesn't make any sense. What does it mean to do? Or in our context, it'd be like percolation in 5.99 dimensions. It's like, okay, what does that mean? And, I'd say that interpreting what that means is the least problematic aspect of this whole thing. I mean, there are a lot of difficulties that one would encounter in trying to make sense of everything. But they're able to do some computations at like a formal level and to say, okay, we can't understand maybe 5-dimensional percolation, but we could understand formally how the exponents would change if I start moving a little bit below the critical dimension of 6. And so I'll give these exponents their names. So all the exponents have these sort of standard names, by the way. And if you want to work on these things, it's really useful to learn the standard names that they have. Partly because this was all worked out by Fisher, so that if you use these standard names, you can easily compare exponents across different models and things like that.
Sorry, Tom.
Yeah.
There is a question from the audience. I will let Andrei Sakar speak. Andrei?
Thank you. Thanks. Hi, Tom. So the question is about, you talk, I think, about problems in moderate dimensions, 3, 4, 5, and 6. What happens in between those integer numbers, say if the dimension is non-integer? Is there anything special?
I guess that's what I was about to say about anyway, actually. So
Thanks.
There's a question of what you mean by that, right? You know, if you look at what physicists mean by that when they're doing this epsilon expansion, they're not really defining an intermediate dimensional model. They're just saying you can write down the calculations that you would like to do to understand your d-dimensional model, and eventually, once you're enough in the mode of doing calculations, d is just a parameter, and it just makes sense to vary it like formally within the computations. They're not really defining a model. That's my understanding of what they're doing. For us as mathematicians, of course, we would like to have like as probabilists anyway, you know, I would like to have an interpretation of what this means. And, you know, you might think, maybe I want to do percolation on fractals, right? Like maybe I'll do percolation on the Sierpinski carpet or something. And I would say, that's an interesting thing to do. You know, by all means, it sounds like a hard problem, but it's probably not the right thing to do to understand things like this. Partly because fractals have many. One of their characteristic features is that different notions of dimension are different for a given fractal, and it's not clear which notion of dimension is correct. And in fact, probably like none of the standard ones are. So yeah, I would caution against going in that direction. I mean, again, I think it's really interesting to study percolation on fractals, but it's probably not the right thing for this story. Okay.
But and I'll say still holds just this, that the problems that are different, higher in dimensions, higher than 6 and 2 or similar, are different between 3 and 6, even if the dimension is related to fractals. So
certainly the behavior will change whenever you change the dimension, and it will be interesting in dimension less than 6. And in fact, for that question of whether the critical behavior is mean field or not, it should always be the spectral dimension of the fractal, which is the right thing. So in that case, I think there's a clear answer. So spectral dimension less than 6 or bigger than 6 should mean mean field behavior, but not that anyone has proven any theorem like that. Okay, so I'll talk more about these things in a second. I mean, I'll eventually start talking about long range percolation. Actually, I think it starts on the next slide. One of the motivations for that will be to have a different setting where we can make sense of this kind of thing. Okay, a couple more comments about these expansions. So one thing, if you're paying very close attention, you might have noticed that, well, so as we change eta, so eta is like the correction to Green's function scaling for the 2-point function. As we change eta below 6 dimensions, the epsilon coefficient is -1/21, and for delta it's 2/7. And if you have a good memory, you may remember that these are the same numbers that appeared on the powers of the log here. And in fact, this is a general phenomenon. So not just for percolation, that understanding the powers of the log at the critical dimension is very closely related to understanding how these exponents are changing to first order as you start to go below the critical dimension. So that's one comment. The other is that you can probably tell these expansions are getting pretty complicated, right? I mean, even the epsilon squared terms are pretty complicated, and they get very, very complicated very quickly. So even within physics, it's not like they're writing down infinite series. And, you know, it's more like if you compute the next coefficient, you can write a paper on it. And there are people who do this, and they're just horrific. I mean, I guess some people love that kind of stuff, but, you know, for me, it's very, very scary. I wouldn't want to do that. Another thing is that these theories are actually expected to be divergent. So even if you kind of dream of doing this to infinite order and so on, you're not going to be able to just plug in epsilon equals 3 and compute the three-dimensional exponents. You'd have to do some kind of resummation technique, which probably involves looking at complex values of the dimension and things like that. And there are even doubts about whether the standard resummation techniques work. So there's a lot of like really hairy stuff if you wanted to really implement this whole story. I mean, it seems well, actually using this to compute exponents in 3 dimensions or something seems very, very far away. I should mention in physics, there is also now a different way of understanding 3-dimensional critical phenomena. As far as I know, hasn't really been applied to percolation yet. And in fact, percolation from this conformal field theory point of view is not the best behaved kind of model for them. But for 3-dimensional Ising, it's been studied a lot. And there's this new technique called the higher dimensional conformal bootstrap. And I won't say much about it, but it's exploiting conformal invariance in 3 dimensions. And for 3D Ising, they're able to get, using this method, which is still, partly heuristic, to get the critical exponents to 10 decimal places. So it still doesn't give exact values, but it gives values that are as accurate as you might ever reasonably want. Okay, I guess mathematicians, we like exact values, so perhaps that just means we're unreasonable at it. I don't know. Okay, so I now get on to the real topic of my talk, which is long-range percolation. So what is long-range percolation? So in nearest neighbor percolation, we started with our lattice, ZD, right? And we just said vertices that are next to each other in the lattice can be connected by an edge. In long-range percolation, we're going to still start with our lattice ZD, but now we're going to say any pair of vertices can be connected by an edge. And again, they're still independent, but with probability that decays as the vertices get further away from each other. Okay. And the interesting case to consider is going to be when the edge probability decays as a power at the distance. And we'll write the power minus d minus alpha like this. So alpha is positive. The notation I'll justify a bit more in a second. So the exact formula we use is this 1 minus exponential. You can think this is the same as taking a Poisson process of edges with this intensity. So beta is the parameter that we vary, so exactly like we varied P in the normal percolation model. Larger beta means more edges. It's not changing the decay rate, just changing the intensity. Okay. And we work with positive alpha. So in other words, the exponent is strictly smaller than minus d. This makes the expected number of neighbors at the origin finite. If you had negative alpha, that would be infinite, and then you would get like beta c equals 0, which is not interesting for us. Okay, so just like we defined PC before, we can now define beta c. So we think about this alpha being fixed. Beta c will be the infemal value of beta where infinite clusters exist. And so, of course, the first question again is, when is this finite? Well, if the dimension is at least 2, it's always finite. There's just an easy comparison with nearest neighbor percolation, where you just have more edges here than, I guess, in nearest neighbor percolation, where P is 1 minus e to the minus beta. Interestingly, though, in 1 dimension, for long-range models, you can also have phase transitions in 1 dimension. So in fact, beta c is also finite when d is 1 and alpha is less than or equal to 1. Okay, and one thing I should stress generally is, I said in 1 dimension, nearest neighbor percolation is really not interesting at all, really. That's no longer true for long-range models. And you can think that the topological features of 1 dimension that make it not very interesting for short-range models, they don't really appear in the same way. Once you have long edges, right, you kind of lose the topology of the space. And, that's also true. Many of the things that made 2 dimensions special and more tractable for nearest neighbor models, like, don't really apply anymore to long-range models. So you lose the topological features of the plane. Now, one reason, I'll give a few different motivations you might want to study long-range percolation. One of them, which I didn't write on the slide, is of course, you might just have like a modeling reason that you're interested in models with long-range interactions, right? Like maybe you're doing some, epidemiological modeling. You're looking at the spread of disease. It's very, very reasonable that diseases can spread, not just to your neighbors, but to anyone living near you with some long jumps. Another reason is that it turns out that we have this parameter alpha now, which is describing how long range the model is. So smaller alpha is more long range, and it turns out that varying alpha is roughly analogous to varying the dimension. There are some caveats here, and it's a bit related to the warnings I was giving about fractals. But you can define something called the effective dimension, which is the maximum of d and 2d over alpha. And in fact, this is, if you know what this means, it's the spectral dimension of the random walk with this jump kernel. And this, it's not perfect. In the case where it's low, you should not expect two models with the same effective dimension to have the same percolation critical behavior. It's not as good as that. It does give us the right answer for when you have mean field critical behavior or not. So it will still be the right thing. The percolation critical behavior should become simple when now the effective dimension is strictly larger than 6. But notice that as alpha goes to 0, the effective dimension diverges. So we can have high dimensional behavior in any dimension. And in low dimensions, we can tune alpha so that the effective dimension is just slightly smaller than 6 if we wanted to get into this epsilon expansion stuff. I won't really be talking about that actually. For percolation, we haven't done these expansion type things yet. I should mention there are some cases where people have done rigorous versions of the epsilon expansion in the context of these long-range models. So, for example, there are works by Gordon Slade, some by himself and some with co-authors, Martin Lohmann and Ben Wallace, studying this in the context of the spin-ON model. Okay, so what kind of questions are we interested in long-range percolation? Well, first of all, we can ask all the same questions we asked before, right? Critical exponent, scaling limits, so on. Now, an additional question that appears that we didn't have before is, well, when is the model genuinely different from the nearest neighbor model? It's plausible as I increase alpha, the model is getting less and less long range, right? The edge kernel is decaying faster and faster. Presumably, when it's large enough, it just doesn't really make a difference anymore. You have the same large scale critical behavior as the nearest neighbor model. So when is that? When does that change take place? Can we understand this transition between what I'll call effectively long range critical behavior? So when having these long edges really changes the large scale critical behavior versus effectively short range critical behavior, which is happening when it's no longer really changing that. Of course, you can ask the same questions for the random walk, right? So you can do a random walk that instead of jumping between nearest neighbors, it does these heavy-tailed jumps. And in fact, alpha, the way I've written this down, this alpha corresponds to like the number of moments that random walk has roughly. So if alpha is larger than 2, that means that this random walk with jumps proportional to this has finite variance. And we know it's very classical probability theory, right? You have a random walk. As soon as it has finite variance, you have the central limit theorem, you have convergence to Brownian motion, etc. It doesn't really matter anymore. The fact that it can make big jumps, it's having the same large scale behavior as if it was only making bounded size jumps. Whereas when alpha is less than 2, strictly less than 2, these long jumps are really having a big difference. And in fact, if you take the scaling limit at the random walk, it's no longer Brownian motion. It's an alpha stable Levy process. So it has a scaling limit which is discontinuous. And this alpha, one reason I should say, in the long range percolation literature, there are a few different conventions one sees for how to write the power of the kernel. I use this one is the best when you're working at criticality, I think, and it corresponds to alpha being like the same alpha as in a alpha stable Levy process, if you're familiar with that. I should mention for random walk, another thing that happens is you could look at alpha exactly equal to 2. So there you're right on the boundary of this change between Levy process scaling when alpha is less than 2, Brownian scaling when alpha is bigger than 2. And, just as we saw when we're talking about critical dimensions, you get a similar kind of thing happening where for the random walk with alpha equals 2, it still converges to Brownian motion actually, but with some logarithmic corrections to scaling that you have to put in. Okay. I guess I'm coming up on the actually, it just exactly hit the hour. Maybe this is a good place to take the break.
Okay, yeah, let's have a short break. 5 minutes?
Yeah.
Okay. Let's have a 5 minutes break. If you have any questions, you can ask them now. Please raise your hand. Whoops. All right, let's have a 5-minute break.
Okay, I guess we are ready to restart with the second part of the seminar. And yeah, please, Tom.
Great, thank you.
Thank
By the
you.
way, I should say somehow every time I give this talk, I go a bit slower again. Well, now I added it in these videos as well, especially for today. But I think this is supposed to be like halfway through my 1-hour talk, but it's ended up being halfway through my 2-hour talk. So anyway, we'll see. Hopefully we're learning some interesting things anyway. Okay, so as I was saying, I gave you 2 motivations to study long-range percolation already. One was just a modeling perspective. Maybe you care about long-range models for some reason. The other was that it gives us this setting to think about varying not the dimension continuously, but the effective dimension continuously. But for me, I think the most motivating thing I found about these long-range models is that they're a setting where you have critical behavior that it's similarly interesting, similarly rich variety of things to understand as in nearest neighbor models. But surprisingly, we can actually prove a lot more about long-range models than about nearest neighbor models, at least in some regimes. And it tends to be these special techniques that only work for long-range models. They tend to work, unsurprisingly, they tend to work better the more long-range the model is, so the smaller alpha is. And so the first really nice example of this is a theorem of Noam-Burger from 2002, who proved that the phase transition is continuous. Again, that means there are no infinite clusters at the critical point whenever alpha is strictly smaller than d. Okay. Now, of course, this is something we would really like to be able to prove for nearest neighbor models. And one thing I should stress here, it requires alpha is less than d. So it's a small alpha condition, but it's actually a very weak small alpha condition. So, in 3 dimensions, for example, this corresponds to like the random walk having an infinite third moment, basically, which is not terribly strong long-range condition. And you can imagine once you get to dimension 5 or something, it's a very weak condition. Now, what we believe to happen is that once you're in dimension at least 2, you always have a continuous phase transition. Although, doing that for very large values of alpha might be just as hard or even harder as the nearest neighbor problem. On the other hand, in 1 dimension, Burger's result is actually optimal because it's an older theorem of Eisenman and Newman from 1986 that you actually have a discontinuous phase transition in this boundary case d equals alpha equals 1. So that means that there is already an infinite cluster at the critical point for these models. And you can think, this point d equals alpha equals 1, it's right on the boundary of when you have a phase transition at all. So if alpha is strictly larger than 1 in 1 dimension, there's no phase transition. So you're getting a special behavior that's occurring only on the boundary of when you have a phase transition at all, and then you're having this discontinuous phase transition. Okay. Now, I'll give more examples soon of things we can do for long range that we can't do for nearest neighbor. But of course, you can also take methods that were developed for nearest neighbor and apply them to long range models, right? So in particular, the lace expansion, which is this method I mentioned for proving the simple mean field critical behavior in high dimensions, has also been successfully applied to long range models in high effective dimension. Again, it has the same caveats as before in that it requires some numerical assumptions on exactly what the edge kernel is and things like that. So, and this was done first by Heidenreich, van der Hofstad, and Sakai in 2008. I'll mention as well that there's an additional case that's something slightly surprising happens, which is if you're in D equals 6, alpha equals 2. So in this case, the effective dimension is actually equal to 6. But it turns out that because of these other marginal effects you have from alpha being 2, something slightly funny happens, and you actually have exact mean field behavior in this case, even though the effective dimension is exactly 6. And this case has also been analyzed for spread out models, like again with these numerical assumptions by Chen and Sakai in 2019. Okay. Now, my first foray into this topic, which is 4 years ago now, actually, it was, this was a sort of pandemic era project for me, was I proved a quantitative version of Berger's theorem, showing that, so he proved that there's no infinite clusters at criticality, but nothing about the distribution of the finite clusters at criticality. In my paper, I showed that you have some power law bounds on the probability of the origin being in a large cluster. And I should mention, by the way, for about as long as this seminar has been running, we started running a specialist seminar in percolation called Percolation Today, which is also still, a pandemic era Zoom seminar that's still trucking along years later. So, well, first of all, I'd encourage, I'm no longer an active organizer, but it's still going. And if any of you who like attending One World, you should also feel free to come along to Percolation Today. So, although I have a feeling they've now scheduled at the same time, so maybe I shouldn't be advertising it here, but it used to be at a different time. Anyway, I should say as well that I've given a lot of talks over the years as I've written more and more papers on this topic. So if you want to see more details, you can look at those old talks. Anyway, so this paper, the first one I wrote, it was proving power law estimates, so getting bounds on exponents, in other words, but not optimal ones. And to write this paper up, I had to write the introduction, so I had to figure out, okay, what is it that physicists believe are actually, like, what do they conjecture about the values of the exponents, really? And I discovered, I had no idea about this, although certainly there were people in our community who did know about it, that there's an amazingly simple prediction about the exponents for long-range percolation. And even in the even for these models which are like intermediate dimensional, so they're not mean field, they're not planar, they're otherwise hard to understand, some of the exponents for long-range percolation have a very simple explicit conjectured value. Not all of the exponents, but some of them do. And so this is the conjecture of Sack that I'm about to tell you. I should say Sack's prediction was really for the Ising model, but as with many of these things, they're not very model specific. Okay, so here's the idea. So we want to understand eta, which is the exponent for the two-point function. Okay, so again, it means that this scaling relation is supposed to hold. Okay, we want to understand if we fix D, and let's say for the purposes of drawing the graph that D is 2, 3, 4, 5, and we want to understand how does this change as we vary alpha. Okay, now the first thing that's reasonable to guess, I should say, Sack gave a much better derivation of his prediction than I'm going to give you. I'm just going to explain what the conjecture is, and there'll be a step that's totally unjustified. So I should say, that's not what he did. He had better reasoning. But okay, so the the first thing to say that's reasonable is that, well, if we make alpha really large, so the model is really not very long range, eventually you should have the same large scale critical behavior as the nearest neighbor model. So let's call the value where that kicks in alpha C. This is often called the crossover value. Okay, so once we, whatever this number is, once we exceed it, we should have the same exponent as the nearest neighbor model, which of course in dimension 3, 4, 5 is something difficult to understand, but whatever it is, we should just fixate there. Now, on the other hand, if alpha is very small, well, then we have large effective dimension, right? So that we should behave in a mean field way, which again means that percolation should behave like branching random walk. But of course, it's no longer the nearest neighbor branching random walk, it's the heavy-tailed random walk, right? Branching random walk, right? That's making these jumps with kernel minus d minus alpha. Okay, so the right thing to compare to is not the Brownian motion Green's function, it's the Levy process Green's function, which decays like minus d plus alpha. So the edge kernel is like minus d minus alpha, the Levy Green's function, the sign of the alpha flips minus d plus alpha. Okay, so in other words, if we plot that guess on this graph, it's just this 45-degree line, right? 2 minus theta equals alpha. Okay, and you know, this should hold when the effective dimension is strictly larger than 6, right? That's when we should get this mean field critical behavior. And the conjecture is that to get the whole curve, you just join up these two lines continuously. Okay, so it's really, again, he didn't just say that. He gave a justification that I'm not going to tell you, but that's the conjecture. So it's really extremely simple. Of course, there is some complexity hiding in this picture in that the location of this corner is at this value. Well, it says if the conjecture is true, then the crossover to effectively short-range behavior occurs when alpha is equal to 2 minus the nearest neighbor value of eta. So that's a complicated number. And indeed, in high dimensions, it will be 2. So the crossover from long range to short range is the same as for random walk in high dimensions. But in low dimensions, it's a bit different than 2. So in 2 dimensions, we have the exact conjecture that it should be 43 over 24, which is a bit smaller than 2. And in 3, 4, and 5 dimensions, it's numerically a little bit larger than 2. And so one thing to note about this graph, of course, is that actually nothing changes as I cross effective dimension 6, right? It's just a straight line, nothing special happening. Now, if you look at other exponents, we know that we should be seeing some distinction between the low and high dimensional regime. And so, for example, another exponent you can get an exact conjecture for from the SAC conjecture, plus these hyperscaling relations I was talking about earlier, is delta. So that's the exponent for the volume tail. And in high dimensions, delta is 2. That's the mean field value. Above alpha C, it should fixate at whatever its nearest neighbor value is. And in between, you can derive from SAC's prediction this conjectured value d plus alpha over d minus alpha. So it's a simple rational function. Okay, so here we do clearly see these changes occurring, points of non-analyticity, in fact, non-differentiability in this curve at these two special values, d over 3, which is when the effective dimension becomes 6, and alpha c, which is when you cross over from effectively short range to effectively long range behavior. Okay. Let me skip this actually. Okay, so let me finally get onto some theorems after too long. Well, some newish theorems anyway. So the first thing we were able to do a few years ago now, which was so I want to start saying, okay, what can we actually prove in these SAC conjectures? Okay, so the first thing I was able to do was to show that this upper bound on the 2-point function. So maybe let me explain with this graph. Right, so we expect this conjecture that I just was writing, right, is that the curve has this shape where it's a 45-degree line until it turns off and becomes a horizontal line. And what this theorem is saying is that that 45-degree line that continues on forever is an upper bound on the true value of the exponent, which of course is consistent with this conjecture. So precisely it's saying that if you average x over a ball of radius r, the 2-point function is on average bounded by r to the minus d plus alpha, which SAC is telling you that should be the correct scaling in the effectively long-range regime, but not in the effectively short-range regime. But it always holds as an upper bound. Okay. I think given the time, I won't really have time to tell you about the proof, but maybe let me say one thing about this, which is all of these results I'm going to tell you about long-range percolation on ZD. In every case, we first proved a result for a simpler model called the hierarchical model, which is easier but not easy to study. It has very similar critical behavior, at least in the effectively long-range regime. Basically, these hierarchical models, they're always effectively long-range. They don't have the transition to effectively short-range behavior. Okay. Now, I wrote this paper in early 2022. I think I posted this in like February or something, and then maybe in like April. So I had a problem at the end of my paper, of course, find some sufficient conditions for a matching lower bound to hold, right? The most natural problem. And it took like 2 months for Noam Berger and his then student, Johannes Baumler, who's on the job market now, by the way. He has many other nice results besides this one, to prove a matching lower bound for when alpha is strictly less than 1. And they have a weaker bound for other values of alpha as well. Okay, so if you take these two results together, what they say is actually that when alpha is strictly less than 1, you really do have this r to the minus d plus alpha scaling of the 2-point function, at least with these spatial averages. Now, this averaging thing is like an artifact of the proof. It's actually really annoying when you want to apply this. And I was later able to improve this to a pointwise estimate. So for every x, when alpha is less than 1, the 2-point function is up to constants, norm of x to the minus d plus alpha. Okay. And you can think these things are telling you in particular that alpha c is at least 1. So together, these two results, first of all, they completely settle the one-dimensional case of Sachs conjecture. So I didn't say what that was actually, but of course, it's just that you only have this first line in one dimension where there's no short-range thing going on. So it just continues up until alpha is 1, and then there's no phase transition afterwards. So these results completely settle the one-dimensional case of Sachs conjecture. And they also give an analysis, well, of course, in any dimension for alpha less than 1, but let me highlight that in 2 dimensions, that includes this interval 2/3 to 1, where the model is not mean field, so it has a low effective dimension. Okay, so again, to summarize, basically, the true curve, it takes the corner somewhere here, somewhere complicated, and we upper bound it by the straight line that continues forever, and lower bound it by the curve of the same form, but where the corner is at 1. Okay, so that's where things stood as of 3 years ago. Now, one thing about this, again, is that this 2-point function, according to Sachs' prediction, which we can partly verify now, it doesn't see the distinction between low and high dimensions, but I spent the whole first half an hour of the talk telling you how important the distinction was between low and high dimensions. And indeed, if we want to go further, go beyond the 2-point function, we need to start understanding things which are changing between these different regimes. And so now for long-range percolation, we have these 2 parameters, if you like, the dimension d, which is an integer, which is why this drawing looks complicated with these step functions, so on. Right, this is the real picture, but let me switch to the simplified cartoon version to explain to you. So, we have d on the horizontal axis, we have alpha on the vertical axis. And as we vary both of these parameters, well, we have 2 different switches we can turn on and off somewhat independently of each other, which is the model mean field? Does it have the simple high-dimensional branching random walk-like critical behavior, or does it have some more complicated low-dimensional critical behavior with hyperscaling and things like that? And then separately, is it effectively long-range, meaning it's really different than the nearest neighbor model, or is it effectively short-range, meaning actually it just looks the same as the nearest neighbor model? And basically, the conjectured phase diagram of how these change looks a bit like this. So, the only complicated thing here is this curve here, which separates the effectively short-range and effectively long-range low-dimensional regimes computing this is like equivalent to computing the eta. If you believe Sachs conjecture, it's equivalent to computing eta for the short, like nearest neighbor models in low dimensions. So that's hard to understand. But other than that, these curves are explicit. And so we get these 4 different regimes, and then we also get all the boundaries between them where we expect further complicated things to, log corrections and stuff like that. Okay. And the very brief summary of the new work that this talk is in principle about, although I've wasted a lot of time telling you about all things, is that we can understand the model very well, like almost as well as you could hope to for many things, for a lot of these regimes. So the regime that we do not understand still, which of course seems very hard, is the effectively short-range low-dimensional regime. So that's when you should have the same critical behavior as the nearest neighbor models in 2, 3, 4, 5 dimensions. Okay, that of course seems very hard. Although I should stress this theorem of Berger about continuity at the phase transition, this applies to like a large chunk of this regime. I mean, this line alpha equals d is like this one here that's tangent to this curve down here. So, it actually, we can prove continuity of the phase transition for models that conjecturally are in the same universality class as nearest neighbor percolation in dimensions, in every dimension, 2, 3, 4, 5. But really understanding critical behavior there properly seems very hard. And, the boundaries of that regime, like this one where you're low dimensional and you're just on the boundary of long or short range, and there should be some log corrections to being the short range. That's probably even harder to understand than the nearest neighbor models, I would guess, though who knows. And then there's this line here where d is 6 and alpha is bigger than 2, where you're short range critical dimensional. We also don't know how to understand that. But every other regime we can analyze now. So, that includes these high dimensional regimes, which of course you can also study with the lace expansion, although our new method has some advantages over the lace expansion that I'll describe soon. But we can also analyze the long range critical dimensional regime. So this d equals 3 alpha less than 6. So when you're effectively long range, but the effective dimension is 6, where we'll get logarithmic corrections to mean field scaling. And we can also understand this regime, the low dimensional regime, where you're effectively long range. With the main caveat being that we don't know where that regime is, right? We don't know what the boundary of the regime is, but we'll be able to define what it means to be in this regime and then understand things in a lot of detail subject to that. Okay, so let's say some theorems. Okay, so we'll start with high dimensions because it's easiest. Okay, and basically what these theorems are going to say is that we have the same critical behavior as the appropriate long-range branching random walk when we're in the high effective dimension regime. Okay, so the condition here is that d is strictly larger than 3 alpha. And going back to the drawing, you should imagine just extending this line up into this quadrant like this. And so this theorem is saying if you're below this line, so it includes the whole effectively long-range high-dimensional regime, everything on this line apart from this point where all the curves meet, and a bunch of the effectively short-range regime. Throughout this whole regime, we can prove this mean field critical behavior. So for example, the volume tail is 1 over root n, and the scaling limit of the model is this integrated super Levy process, or super process. So you should think, again, that just means it's the same scaling limit as the branching random walk. And in contrast to every time I mentioned the lace expansion, I said, oh, there are some caveats. I'm not telling you exactly what they are, some numerical assumptions. There's nothing like this. This is really the theorem that I'm showing you. So if you know that d is strictly larger than 3 alpha, that's all you need. None of this spread out model kind of stuff that you do with the lace expansions. This is a completely non-perturbative theorem. Okay. Of course, the only thing that's not optimal here is that it doesn't apply in this large alpha high dimensional regime. Okay, so in this theorem, you do also see this transition between the effectively long range and short range behavior. So when alpha is smaller than 2, well, okay, so the way I'm taking the limit here, I'm thinking of the cluster as a measure, right? So I'm summing these Dirac masses over the cluster at the origin, rescaling that by n, conditioning the cluster to have size at least n, and then rescaling the distances by some scaling factor. Okay, and when we change alpha between as alpha crosses 2, the nature of the scaling factor changes, and the limit object also changes from being like a super Levy process where you're having big jumps to a super Brownian motion where it's all the infinitesimal particles are moving continuously. And I didn't write it down, but we can also analyze the case alpha equals 2, where you have logarithmic corrections to the super Brownian scaling. Okay. Now, of course, this is great, other than that we would like to ideally be able to understand the whole high dimensional regime and not just a bit under this line. And we can sort of do that, so it's not quite as satisfactory, but if alternatively you're above this line, but you know that you're in high dimensions and you have the outputs of these more traditional perturbative methods like the Lace expansion, then you can run the rest of the proof. So currently we can't get it to start from scratch, so to speak. But if you have some relatively weak inputs that you can get from these other methods, then you can get the full strong results, everything here about full scaling limits and things like that. Okay. Good. So, I think one of the really nice things here, again, to stress is that we don't have this perturbative nature, the small parameter numerical assumptions that were always needed to do the old methods like the Lace expansion. And this is very much related to being able to handle the critical dimension as well, because it's sort of known that these techniques like the Lace expansion, they just can't handle the critical dimension, whereas these new methods can, at least in the effectively long-range regime. And in fact, we can completely understand everything to just as much detail as in high dimensions. So if you're on this line, d equals 3 alpha less than 6, so again, that's the effectively long-range critical dimensional regime. We can compute many things, actually. I'm just telling you like a few of them to put on a slide, but in particular, the volume tail is like the fourth, it's larger than the mean field scaling of 1 over root 10 by the fourth root of log. And the scaling limit is the same as it is in high dimensions. Once you put an appropriate log correction, you have to put that into the scaling to make the limit come out correctly. Okay, and again, this is completely non-perturbative. There are none of these small parameter assumptions, which are also needed in like traditional approaches to critical dimensional stuff that have been done, for example, by Bauer-Schmidt, Bridges, and Slade doing the 5-4 model. Okay, let me just check the time, sorry. Okay, actually still have quite a lot of time. Mm-hmm. Okay, good. So maybe rather than telling you about low dimensions now, let me come back to that in a few slides. Okay, so I was just mentioning, there have been previous work successfully analyzing critical, like logarithmic corrections to scaling at the critical dimension, just not for percolation. I think one of the most prominent examples of this in probability is this big series of works by Bauer-Schmidt, Bridges, and Slade from about 10 years ago now, where they analyze something called the 5-4 model. It's not particularly, I don't want to write down the definition of the 5-4 model. It's a bit like the Ising model, but a bit different. And the key feature that this model has is that you can think of it, I was explaining to you at the beginning how we can think of percolation as being like a self-interacting version of branching random walk. And this 5-4 model, whatever it is, you can think of it as a self-interacting version of the Gaussian free field, right? So the Gaussian free field is this other very canonical model in probability. It's the Gaussian field on the lattice where the covariances are the Green's function. And basically, what they do is they implement a rigorous version of this renormalization group analysis, which, for decades was the main way physicists understood critical phenomena, since it was actually not introduced, but sort of brought to maturity by Wilson in the 70s. And Wilson won a Nobel Prize for his work developing the theory of the renormalization group. And one thing, one clarification immediately about the renormalization group. Just forget that it has the word group in it. It's not related to the mathematical notion of a group. The other thing I would like to clarify is, we often do renormalization type arguments in probability that involve some kind of coarse graining or something like that. And the renormalization group tends to be something a bit different than that. That doesn't, it potentially can involve some coarse graining, but it often doesn't. In fact, it won't in the examples that I'm talking about here. So the way to think about it instead is you want to introduce some kind of cutoff. And now what exactly that means, it can mean a huge number of different things. And a lot of the art of doing the renormalization group is like picking what exactly you mean when what are you doing when you introduce this cutoff. So in this example of the phi-4 model, the way they're doing it is instead of looking at the GFF plus this interaction, they replace their GFF with like a finitely dependent version of, so saying, instead of looking at the field where the covariance is the Green's function, you replace the Green's function with something finitely supported. Now, the exact way that you do that is super important for the analysis, and they have a very nice way of constructing these finitely supported approximations to the Green's function that come from looking at the wave equation or something. And again, there's a lot of art that goes into exactly how you do this. But the point is you replace the GFF with this field that has finitely supported covariances. So in other words, the field just becomes independent beyond some distance. And then you try to understand, okay, how is the model changing as I increase this finite range of independence? And you can hopefully believe that if you understand the asymptotics of that well enough in various senses, then you can go back and deduce something about your original model. And this is something that, as I said, in physics, this has been a massively successful thing for decades, and it's versions of this are done in many other fields in probability as well, like SPDEs. And for these phi-4 models, it was implemented very successfully by Bauer-Schmidt, Bridges, and Slade. Okay, so one problem with doing this for percolation is that it's just a different kind of model. Like, it's not the GFF plus an interaction, it's a branching random walk plus an interaction. And in fact, if you look at I mentioned these heuristic papers in the physics literature on 6-dimensional percolation and 6 minus epsilon dimensional percolation. And none of these are really studying percolation, actually. They all study a model which is not even defined, which is like a zero component phi cubed model. So you have some other kind of spin system or field theory, but then you set the dimension of the spin space to be 0, which of course doesn't even make sense. And then they analyze everything there. And for percolation, we just don't know how to make that bridge between percolation and a field equivalent field theory rigorous. Okay, now a different setting where that has been done rigorously is self-avoiding walk. So, and this is used in the work of Bauer-Schmidt, Bridges, and Slade. They didn't do this. This was already known, but there is a rigorous way you can make sense of the similar physics prediction that self-avoiding walk is like a 0 component phi-4 model, like a phi-4 model with 0-dimensional spin. Now, of course, that doesn't make sense, but it turns out you can make sense of it in terms of a supersymmetric version of the phi-4 model. Anyway, I'm not going to get into this, but you can make sense. These things have been done successfully for some other models, but for percolation, we don't know how to do this. Okay, and this is a basic problem if you wanted to apply this framework to percolation. We just don't know how to transform it into a field theory, which is sort of the starting point of all of these analyses. Another problem with the way these guys like to do their analysis is when you start with your phi-4 model and then you truncate the Green's function in the GFF and so on, these intermediate models you get, they're just horrific. They have the phi-4 model is reasonably nice. It has lots of nice probabilistic properties, a bit like Ising. These intermediate models are just horrible. They don't have any properties at all, basically because these approximating things you get, they have some negative entries. So these intermediate models are like not purely ferromagnetic. They're like mixed ferromagnetic, anti-ferromagnetic. Anyway, they're not nice models. And so this forces you to like not really use any of your probabilistic tools and to work in a very analytic way where you're just saying, okay, you know, I want to say my thing is a small perturbation of the GFF and it remains a small perturbation as I scale up, something like that. And so in particular, this leads to these kind of perturbative results in the same vein as the lace expansion. Okay. So in this new work, basically the main point is to develop a version of this renormalization group analysis that first of all works directly with percolation. And I should say it also works directly with many of our other favorite models in probability, like self-weighting walk and Ising and things like that. And it's a way of analyzing those in a much more probabilistic way, still with this flavor of doing this renormalization group analysis, but without, there's no supersymmetry, there's no passing to equivalent field theory. It's going to directly analyze the model that we care about. And the big downside is that it's only going to work for long-range models. I mean, that's obviously a huge downside that they didn't have with this other approach. But it's extremely simple to explain what it is. So if I'm talking too much physics, you know, in an attempt to motivate you, if that's not working, if you're being demotivated by me saying too much physics, then start paying attention again now, because I'm going to tell you how we actually prove things in it, and it's very simple. Okay, so here's the idea. So first of all, okay, so, you know, I told you how to define long-range percolation with this specific kernel, the distance, the minus d minus alpha, but of course you can define long-range percolation with any kernel exactly the same way, right? And what we're going to do is to slightly change the kernel we're working with. This is just a constant rescaling. I'm going to think of my kernel rather than the distance, the minus d minus alpha. I'm going to think about it as the integral of the power one smaller from the distance to infinity. Okay, of course, these are the same up to a constant. Okay, now what we're going to do, as I was saying, in RG, you want to have some notion of cutoff that you then send to infinity and then study the asymptotics. And we're going to do this in a very simple way. We're just going to cut off our integrals at some scale r. Okay, and just for this indicator is just saying if these are the wrong way round, it's 0. It's not a negative number. Okay, that's it. So we're going to define JR to be this cutoff kernel, but beta C is always going to be beta C of the original kernel, not of the cutoff kernel. Okay. And what we're going to do is we're going to try to understand. So we now have this 2-parameter model, right, with beta and R. We're going to fix beta as beta C of the original model. And then we're going to introduce this cutoff and then try to understand what happens as we send the cutoff to infinity. So of course, as R goes to infinity, I'm recovering the critical model. But all of these models with a cutoff, they're actually subcritical. That makes all these moments finite. If I tried to look at moments like this with R equals infinity, that at criticality, they'd just be infinite. But now they're finite, and I want to study their asymptotics as R tends to infinity. And it's hopefully at least plausible that if I understand well enough the asymptotics of moments like this for enough quantities as a function of R, at the end, I can go back and prove something about the problems I originally cared about, right? And these theorems, of course, they didn't reference this cutoff. Okay. So again, what are the advantages of this? Well, I sort of said this already. First of all, this just makes sense for models like percolation, or you know, you can do this with any long-range model, right? Just makes sense. No need to find some weird isomorphism theorem first. And just to say a bit more about what's going on in comparison with like this Bauer-Schmidt-Bridges-Said renormalization group approach, they're kind of dual to each other in that what they're doing is they're applying a cutoff to the Green's function, which is like the inverse Laplacian. And what we're doing is we're applying cutoff to the J, which is like the Laplacian. And you know, this only makes sense in the case where you have long-range models where the Laplacian is like a non-local operator. But in some sense, they're dual to each other. But when you can do our thing, it's much nicer analytically. And you know, the key property is that when you're doing percolation with this cutoff kernel JR, it's still percolation. You have access to all your favorite tools that you're used to using as a probabilist studying percolation. And this is, of course, very useful. The fact that you have all these probabilistic tools and correlation inequalities, things like that, that all goes into the fact that we can do a non-perturbative analysis without any of these small parameter assumptions. And then, related to this, I didn't tell you the theorems yet, but we'll also be able to treat the whole low effective dimension regime, at least when it's effectively long range, non-perturbative, like the whole regime, not something about like, oh, you're slightly below the critical dimension, but the whole effectively long range, low dimensional regime. Although this part of the analysis certainly is using that. One nice thing about this story I'm about to tell you is that the high dimensional part, it really doesn't use very much about percolation. You can just take this argument and apply it to many other models out the box, basically. The low dimensional analysis as it stands seems to use a lot more percolation specific techniques. Okay, so what do we do once we introduce this cutoff? So the key thing that we want to do is to prove, well, as I said, we want to understand the asymptotics of moments and things like that as a function of the cutoff. And the primary way we do that is via establishing asymptotic ODEs. So what I should have done is started with the first moment so you could see a simpler thing and then write down this one. I didn't do that. So the idea is what we prove is that in high dimensions, including at the critical dimension, if you look at the derivative with respect to R of these moments, like for now, let's just look at the moments of the volume of the cluster, they satisfy to first order a simple, explicitly solvable system of ODEs. And you can think this is like a DAG, like an upper triangular system in the sense that if you look at the first moment, it's telling you the derivative of the R derivative of the first moment is asymptotic to beta C R to the minus alpha minus 1 times the square of the first moment. That's what this says in the P equals 1 case. So in that case, you just get the first moment. And in fact, that ODE is very easy to solve, right? It's similar to this F prime equals F squared ODE, it's separable. Then in higher dimensions, when you look at the pth moment, you get something on the right involving the moments up to the pth one. And these are things you can solve explicitly. And just to give you some indication of where this comes from, basically what you can do is you can write, let's just look at the first moment. You can write down an explicit formula for the derivative. So this is using something called Russo's formula, which is a standard technique in percolation. It says you can understand derivatives of things in terms of pivotal edges. So basically what that means is you're imagining the edges are appearing on this R ball. And as they appear, so basically you get this expression for the derivative. It has this prefactor, which just comes from the thing inside the integral, right, defining JR. And then you have a sum over the ball of radius R of this expectation of the size of the cluster at the origin times the size of the cluster of Y times the indicator that they are not the same cluster. Okay, so this is like this Russo's formula pivotal expression for the derivative of the first moment. And what this theorem that I wrote on the other slide is saying is that in high dimensions and at the critical dimension, this asymptotically factorizes, it behaves the same to first order as if these two clusters were just independent. That's all it's saying. Okay, and then you get a similar thing happening for the higher moments. Okay, so it's instructive to compare this with what happens in the more obvious thing to do if you want to analyze percolation, and you can do this in neuroscience models as well, is you just differentiate with respect to P, right? And if you did that in high dimensions, what should happen, although I think this is a provable statement, but it has not actually been proven in the literature, is that as P goes to PC in high dimensions, the derivative of the expected size of the cluster scales like some constant times the square of the expected size, which is very similar to this. Here we have this power of R as well. It's just to do with the different kind of parameterization we have here. But a key difference is that when you do it this way, and it would be similar if you varied beta in the long-range model, this constant is something complicated and inexplicit. And basically, you have a similar formula in terms of, like, you have this edge that's opening up, and you have the two clusters on either end of it, and it's like the expected size of them on the indicator that they're different. And in high dimensions, these two clusters, they don't interact very strongly, so they behave like roughly the same as if they're independent. But they can't really be asymptotically independent because they're right next to each other. You know, they're definitely having some interaction with each other, even if it's not that strong. And so you'll get some complicated constant here that's describing that interaction between the two clusters on the microscopic scale. And moreover, if you're doing this in 6 dimensions, you know, not that we can prove this, but there should be this constant should be replaced by a power of log. You know, whereas what's happening when we do things this way, with differentiating with respect to R, we're looking at a long pivotal edge. So these two endpoints at the edge, they're very far away from each other. And it's actually is possible for them to be exactly asymptotically independent. And moreover, it's even possible for that to happen at the critical dimension, which is what we prove. Okay. I think given the time, I won't be able to say more about the proof, but basically what this theorem is saying is that you have asymptotic independence at the two ends of the long pivotal edge. Okay. Now, once you have this theorem, you can then analyze this ODE, this system of ODEs, and of course the complexity is that it's an asymptotic system of ODEs, right? So you have to worry, okay, is the solution to the asymptotic ODE asymptotic to the solution to the exact ODE, right? And the answer is sometimes, but not always. It depends on the ODE. And in fact, if you look at this particular thing that occurs in this problem, there's actually a different behavior in for p equals 1, p equals 2, and larger values of p. So p equals 1, you get this nonlinear ODE with the square on the right-hand side. In that case, the solution to the asymptotic ODE is asymptotic to the solution to the exact ODE. It works out very nicely. For p equals 2, you get this ODE, once you plug in the asymptotics to the first moment, you get the derivative of the second moment is like 3 alpha over r times the second moment. Now, that's really not telling you very much about the function, actually. It's telling you that it's regularly varying of index 3 alpha. That's all it's telling you, basically. So it's giving you the power at the growth, but it's not telling you anything about logs or anything like that. And of course, that's reasonable because I told you that this equation is true both in high dimensions and at the critical dimension. And, you know, we should be getting some logs appearing at the critical dimension. On the other hand, once you go to p is 3 and higher, things become nice again. And whatever complex like log factors or whatever were appearing in the second moment, they get replicated in the higher moments in a simple way. And there are no kind of new log factors produced. So in fact, you can write down an exact solution, but it involves this unknown, slowly varying function, which will, in high dimensions, be a constant, converging to a constant, and in the critical dimension is this 1 over root log. But, you know, this formula involving the unknown slowly varying function, that just comes from solving this system of ODEs. And the key thing to notice here is you get this double factorial, and that's actually the combinatorial prefactor here is actually encoding the scaling limit. So the fact that you're getting these double factorials, it's telling you that when you take the scaling limit in an appropriate sense, the volume of the cluster is going to have a chi-squared distribution. And that's because the chi-squared is just the square of a Gaussian, has these double factorial moments. Okay. Now, you know, why you get this 1 over root log in the critical dimension, that's a longer story that I don't have time to get into. But to summarize very quickly, the point is that in high dimensions, the errors in this asymptotic ODE are super small. They're small by a power of r. So actually, in that case, it's easy to analyze this and show that this slowly varying correction just converges to a constant, basically because all the errors are small enough. In the critical dimension, the errors are pretty big, which is what's eventually producing these log corrections. And so if you want to compute the log, you have to expand the differential equations to the second order term. You have to do a second order analysis. And one interesting thing is that the way you do that is you first do all the first order analysis. This is actually enough to give you the full scaling limit of the model, but with respect to some unknown scaling factors that involve this unknown slowly varying function. And then once you have that, that actually helps you compute the second order correction. The asymptotics of that are described in terms of the scaling limit. So it's an interesting thing where you have to compute the scaling limit before you compute what you're scaling by to get the scaling limit. Okay. And hopefully it's believable that once you understand everything about the volume in this level of detail with the cutoff, you can figure out how to prove everything about the model without the cutoff as well. Okay. Good. So I'm nearly, or maybe I'm already out of time. I don't know if I go to the hour. Maybe I'll just quickly say, if you want to understand how things sit in space, you can do a very similar thing. You just differentiate quantities that involve where the points are in space. So for example, you can look at the sum over the cluster of the squared Euclidean norm. You can derive in high dimensions an asymptotic ODE satisfied by this. This has two terms in this case, the term that's involving the function you're differentiating, and this forcing term, which basically comes from the length of the pivotal edge itself. And this ODE has a change in behavior. There's a competition between this coefficient of 2 alpha here and the exponent 2 plus alpha here. And of course, these become equal when alpha is 2, and this is ultimately driving this transition between super Levy scaling when alpha is less than 2 and super Brownian scaling when alpha is bigger than 2. And again, hopefully it's plausible if you can do this not just for this, but for arbitrary moments of this kind of form where you sum over a bunch of points and you apply polynomials to all of them, then you understand the full scaling limit through the moments. Okay. Now, one thing that you get from this is that you can compute the correlation length as a function of R. So, when you introduce this cutoff, the model becomes subcritical. So there should be some scale above which connection probabilities, things like that, they start decaying really fast. Right? This is known as the correlation length. And what we find is that in high and critical effective dimension, the effectively long-range regime is characterized by the correlation length when you introduce the cutoff on scale R being of order R. So when in the effectively long-range regime, you cut off on scale R, the model already feels subcritical on that same scale, order R. In the short-range regime, you have to go to a much larger scale before you realize that you did the cutoff. And what we can do is we can actually take this to be the definition of the effectively long-range regime through this particular formula for the correlation length. And just define, because we had this issue that we don't really know where the effectively long-range regime is in low effective dimensions. So we can prove that this does hold exactly when it should in high and critical effective dimension. And we can also prove that it's true for alpha less than 1. And using this now defining the effectively long-range regime like this, turns out our methods are still useful for analyzing the entire effectively long-range regime. And I think I'm basically out of time, but let me flash up some theorems. So for example, we can fully prove the part of Sachs prediction in the effectively long-range regime. So throughout the entire effectively long-range regime, you have this simple scaling, even point-wise, of the two-point function as predicted by Sach. And in fact, it's not on the slide, but you can completely compute point-wise like the three-point function as well if you want. And this has a change in behavior between high, low, and critical effective dimension. We can also verify like the whole heuristic theory of scaling and hyperscaling relations in the effectively long-range and low-dimensional regime. So get a bunch of other exponents as well. And maybe just to end, I'll say one last thing that I think is really tantalizing, which is that in fact in low dimensions we can compute all the k-point functions. So you have k-points, what's the probability they're all in the same cluster, up to constants, and it's given by this weird recursive formula if anyone's seen anything like this before, please let me know. This is, you take a minimum over partitions of the set into 3 non-empty pieces and you product them in square root. Anyway, the one interesting thing about this is that it gives this function, this explicit function defined recursively like this, is conformally invariant in the sense that it should be. I won't go into it. And so a corollary of this is that you have some weak version of conformal invariance for the effectively low-dimensional, effectively long-range models. Where to go next with this is not clear, but I think it's very interesting. So anyway, sorry for going over time, and thank you all again for your attention.
Thank you very much, Tom, for a very nice talk. And yeah, I guess we have still a few minutes for questions. There is, again, Andrei. Probably you can unmute yourself, Andrei, if you want.
Thank you.
Yeah.
Thanks. It was a very, very interesting lecture. So my question in the chat is about, I think you had 3 or 4 slides back, naturally, moments related to approximate. So you had approximate ODEs system, but
Yeah.
my question is, what if those moments, is it possible that maybe they do not exist, the left side, right?
Oh, yeah, they do. Luckily for us, they do always exist.
Okay.
So
Okay.
this is basically a consequence of something called the sharpness of the phase transition. It's a basic theorem in percolation. It says below, when the model is subcritical, which here it is because we introduced the cutoff, you have in fact exponential tails on everything. So you have not just moments, you even have moment generating functions if you want, although we're not using that. Also, you could worry if this is even differentiable, right? But indeed it is, and that's fine.
May I just ask 2 very, very short questions? I hope not to steal time.
Please.
Sure.
Thanks. So shortly, firstly, you mentioned lace expansion as standard here, and one other technique, I didn't understand the name, but what are the alternatives to lace expansion? And secondly, on your, I think, very last slide, you had connection to conformal invariance. Is there any strong connection between percolation and study of, say, SLEs, trivial quantum gravity, random planar maps? Thanks. Related to which are related to conformal variance.
Okay. Yeah. Okay. So let me start with the first question. For a long time, for proving that, as mathematicians, proving mean field behavior in high dimensions, the lace expansion was essentially the only method. There's now a slightly different method that's been introduced by Hugo de Pan and Roman Panis. That it actually has still a lot of similarities with the lace expansion, I think, and it has similar caveats applying to it. You know that you need these numerical assumptions and so on. So it's a bit different than lace expansion, but it's not completely different, really. As I mentioned, the other thing I mentioned maybe was this, like, these rigorous approaches to the renormalization group, which again they've not been successfully implemented for percolation, but they're done for many other models like self-voiding walk and 5-4 model. Of course, renormalization group, it's not really like one method, it's like a lot of slightly different methods, depending on exactly how you do things. But yeah, those are the main things that people have used in high dimensions, and RG is also useful, for example, at the critical dimension. The two-dimensional story is really completely separate. So that's where you have these connections to all the other topics you just listed. So SLE, Liouville quantum gravity, random planar map. Of course, these are all related to two-dimensional critical percolation, like nearest neighbor. And so far, these have been studied with essentially a disjoint collection of techniques from those that are used in the high dimensional case. Of course, it would be very interesting to have some more unified framework. I mean, one of the interesting things in this new work that I'm talking about is that in the end, we're able to analyze, at least for these long-range models, which of course won't converge to SLE or anything like that. But actually, it's a one unified framework, more or less, that you apply to all the different regimes. So I didn't really tell you how it works in low dimensions, but it's actually quite interesting. Essentially, the way you analyze low dimensions is by contradiction. You show that if the exponents don't take the right values, then you can do these asymptotic ODEs that you have in high dimensions. Mm-hmm. So somehow it's a funny thing where you analyze low dimensions using the high dimensional method in the context of a proof by contradiction. Anyway, that's very different to how people have studied the planar models where there are all these connections to SLE and so on. So there are certainly interesting questions about connecting long-range percolation with those things. So, you know, as I was saying, what we conjecture is that alpha C is equal to, you know, you should have this crossover to effectively short-range behavior in 2 dimensions at 43/24. But even showing that if alpha is like extremely large, that you have SLE and things like that in the sky. I mean, that would be amazing. I mean, especially seeing as even for the nearest name models, we can only analyze one model, right? The site percolation on the triangular lattice. So even proving these things for large alpha in 2 dimensions, it's some kind of much stronger universality kind of statement than anything people have been able to prove so far about 2-dimensional percolation. So that's very interesting. Then finally, there's the question of conformal invariance not in 2 dimensions, or for long-range models where they're really effectively long-range. And here, you know, we believe actually that they still are conformal invariants. It's not as powerful outside of the short-range 2-dimensional case because you don't have the Riemann mapping theorem anymore, right? There's no the only conformal maps you have in 3 dimensions, even between 2 open sets, connected open sets, are the Mobius transformations. So you have much fewer of them than in 2 dimensions. But what physics tells us is that it's still really useful. So invariance under Mobius transformations, it's much less powerful than invariance under all the conformal maps that you have in 2D, but it's still very useful. And this is something I would say within our community of like probabilists doing mathematical physics, this higher dimensional conformal invariance is something that people really haven't done any serious work on more or less yet. So it's really in very early stages.
Great. Thanks a lot.
Thank you a lot. Are there other questions from the audience? Doesn't seem so. So I think that was a very two very nice lectures. Thank you very much. And also given the time, we stop here. And thank you, Tom, a lot. And
yeah, thanks for the invitation. It's very nice to speak here.
Thank you. And we resume in 2 weeks with the next seminar. Thank you a lot for coming.
Great. Thanks again. Thanks everyone for coming.